So, welcome you, very mighty three, to your Engineering 101. And this very much is, as the number would suggest, a very general introduction to the world of engineering, one that doesn't necessarily go too deeply into the specifics of one engineering field in particular, but is designed to equip you with sort of a general toolbox that all engineers make use and all require. We'll sort of get to know each other quite well this semester, as we, even with sort of everybody here, there's some noted absences. There are only about 7 or 8 of you, so we'll get to work together very closely, which is quite apt for engineering work. Everything is based on groups. We'll get to introductions and we'll sort of meet each other in a moment, but I'll give you my formal introduction. My name is Professor Sakimoto. Uh, I always like to figure out where people come from. It's sort of a part of who we are. And I was born and raised in Honolulu, Hawaii. I was sort of there for the first 18 something years of my life before sort of coming up here to the US mainland to work and play somewhat. And my qualifications to teach you is that as an undergrad, I was undergrad at Yale University. I was a chemical engineer. There, I did a lot of research on sort of solar energy and photovoltaics. This is an example of a device that we invented and built and published that used SWNT, so single wall nanotubes, carbon nanotubes, as a way to create a very, very efficient, but also very low cost solar cell that sort of harvests electricity and turns into something that we can use. So I have extensive experience in the world of energy and sort of solar energy. From there, I've also done chemistry, so I have a PhD in chemistry from UC Berkeley, and there sort of I spent some time pairing solar energy with biochemistry. So we use a sort of big field of work called artificial photosynthesis, which is designed to mimic and exceed the ability of plants to turn sunlight and CO2 into useful products. And my most notable invention was something we call a bionic microbe, which is we took a bacteria that turned CO2 into various sugars and other types of chemicals, and we put tiny little solar cells on them, about the size of quantum nanodots. We put them on the body of the bacteria, which you sort of see these little bright clusters on the bacteria cell body that allow them to become essentially like plants with little solar cells attached to them. From there, my time here in Boston, I spent some time at Harvard working on the so-called bionic leaf, which sort of extends this idea of turning solar energy into something that bacteria can use and eat. Um, and it worked so well, and I'm good enough of an engineer that we were able to commercialize what we discovered here in the lab and turn that into a company called Kula Bio that's sort of based here in Boston. It's sort of moved out to Natick at the moment. That turns solar energy into a fertilizer. This particular fertilizer is composed of a bacteria that fixes atmospheric nitrogen and produces nitrogen ammonia based fertilizers. Very sustainable, only using solar energy and the ambient air. And that sort of is being pushed out into the world as we speak. More farms each day, hopefully doing good in the world. But my experience very much comes from the world of a chemical and material side of engineering, but inherently, most of us engineers work across many different disciplines. I've worked across structural engineering as part of my work. I've worked, of course, through mechanical and other parts of bioengineering. And so I feel well equipped, and I hope that I've convinced you, or we will learn together how well equipped I am to tell you about this very exciting career path that you've embarked upon. Currently, I do have some research going on in which we try to convert plastic waste into various things, mostly trying to make it more biodegradable. All of these things I'm happy to tell you more about as we explore these aspects of engineering together. So, here's what we're doing today. Normally, these courses, or this particular course, is scheduled to go all the way up until 2 p.m. As we require all of that time, we do take breaks, so this is not an exhausting class by any means. But today, hopefully, I believe we should be able to end a little sooner since we have less to get through. But first, today we'll talk a little bit about course logistics, sort of what we're trying to do here, how you'll be assessed by the end of this course. Again, this being an intro course is very low stakes. This is not here to penalize you if you aren't yet sort of at the top of your engineering game. We'll talk a little bit about sort of what it is that engineers do and sort of give ourselves a frame to think about what skills do we need to learn, what skills do we need to acquire, are we suited in terms of personality to be an engineer. We'll talk more about sort of what types of engineering might be found both here in the greater Boston area, but abroad as well. And then we'll finish off with sort of the first of many group activities, group design challenges, trying to construct a bridge pier out of paper, since it's a good sustainable scale model of real building materials. And we'll practice some engineering and learn some things in the process. So, for this course, we have a few things that we want you to be able to leave with. At a high level, our big goal is that we want you to be confident that you want to be an engineer. Becoming an engineer is a very long process. It's a very tiring process, a very painful process in many aspects because of the expectations and rigor. And you want to make sure that you're confident that you want to set yourself down on this path. If you ultimately at the end of this course decide that engineering is not for you, there are many different aspects of the same creative problem solving that you may head towards, but it's helpful to get an idea of what engineers actually do. As you move through your studies, you'll equip yourselves with a lot of different very specific skills and tools for mechanical and civil and bioengineering, but there is a core toolbox, things that deal with basic science in math, physics, and chemistry, programming tools, group work, project management tools that every engineer will need, and we practice some of those things now. Importantly as well, most of your work as an engineer will be done as a team of engineers, and so practicing interpersonal skills is always very helpful, but meeting fellow engineers and finding people who can join your cohort or your network of engineers is an essential sort of social skill we build now. Granularly, there's a few things that we are trying to impart upon you. A much more extensive list, but we'll highlight some ones that we hamper or that we drill on in particular. We want you to get an idea of engineering as a profession. We want you to understand what it is that engineers do in any sort of big project, whether it's building a bridge, creating a new medical device. Engineers form a particular function within that group. Engineers are usually not the ones who go out and work with patients and sort of surgically implant medical devices. We're not the ones who go onto a commercial to advertise these things to doctors. We're part of a different aspect, the mainly design test part of implementing an idea in the real world. I also want you to have an idea of what it is that engineers are actually actively working on these days. There's many things that we do as engineers that will never go out of fashion. We will always build buildings, we'll always construct roads, we'll always sort of improve infrastructure, but engineers are engaged in many areas of research, trying to fix modern problems that hopefully we can fix within our lifetimes. So to learn about sort of modern engineers, part of our essential toolbox is the math and calculation side of it. Beginning next week, we'll sort of get our hands deep into the practical side of how engineers calculate and perform math, not just sort of abstractly for the fun of it, but really to solve problems and to get good or better estimates of things we want to know, things we call things like back of the envelope or order of magnitude calculations, which are really there to estimate values. Engineers really sit at this weird intersection of science and business, and a lot of what we're driven is not just by what is a good, interesting scientific idea, but what is economically feasible, what will people pay for to improve their lives or the lives of other people. So a lot of our work is not just about inventing fancy bridges, but of course inventing fancy bridges that are affordable, that come in within a certain cost that people are willing to pay for. So we'll deal with and dive into a good aspect of engineering economics as well. Engineers, we really utilize every tool at our disposal, and one quite ubiquitous one that every engineer needs to be very, very versed at are a variety of computational tools. If we aren't yet familiar with spreadsheet calculations using things like Excel, as well as we don't yet have any programming experience with a language like Python, we'll cover both of those throughout this course. Those are much more extensive topics to be delved into, but we'll do a little bit here just to get our feet wet so that you can sort of continue your studies from there. But we're going to learn a lot of computer skills inherently within this course. As I said before, every sort of engineering project is done really as a group project. Very few engineers work on their own. And for anybody who has ever done a group project in school or class and had to deal with other people, other personalities, trying to manage other people and get everybody to do what they promised that they would do or deal with different personalities requires some skill and some thought. And so we're going to directly sort of tackle the idea of how do you work efficiently as a professional group of people, as a professional group of engineers. The most important and sort of largest aspect of what we do is to practice this process of design engineering. How do we as engineers come up with a problem that requires solving and go through a cyclical process of coming up with ideas, testing those ideas, implementing those ideas, and refining from there on. Beyond that, our work as engineers really is a public-facing one. We come up with ideas, we come up with designs, but ultimately our designs are no good if no one ever hears about them, or the general public doesn't understand what it is that we've done or what it is that we've built. And so, towards the very end of this course, we work on sort of these external-facing aspects, thinking about how do we communicate very technical ideas about chemicals and medical devices and bridges and buildings to a less technical audience, to a general public. How do we give public talks to both our colleagues and the lay person? And how do we incorporate an aspect of engineering ethics, which accounts for not just what is the numerically best answer, what is the most efficient way to do something, but one that appreciates that we are humans who are driven to and should be making ethical, moral decisions about what we do with our time and efforts. So that's what we will learn, and we'll get a lot of practice. This is very much a learn by doing course. Logistically, some things to lay out. There is Moodle that we use as our class portal. Really everything will be there and posted. Largely, if there's any reading assignments or things to watch, those will be posted as links or sort of scanned PDFs. I did not elect to have a textbook for this course because they're not quite as tailored to what we do in this course. But importantly, you'll find there as well a list of your homework assignments, of which we have one for this week. We'll talk about that in a moment. And of course, the grades to keep track of sort of how you're doing within this course. There's not really any required materials, but you're very strongly recommended to bring your laptop to each class. Most of what we do will require some sort of computation. There are computers here in case that you forget yours or you can't bring it, but it's very helpful to have your own device so you can figure out how that works. By and large, we'll meet here every Tuesday and Thursday. We'll start at 9 a.m. or as close as we can. We are scheduled to go until 2 p.m., but in many days we'll sort of end our formal required sort of lecture period far before 2 p.m. And the remainder will be a lot of group activity, group work, which may be variable in how long that takes. So do be prepared to stay the full day, but we will not always utilize that time. You, of course, are welcome to bring anything that you need to get through the day, whether it's coffee or food or snacks or lunch. Please do bring that. Unlike any of your biology or chemistry classes, this is a pretty clean space, so you're welcome to eat in here without any sort of worry about contamination. If we have ample time together, and we sort of have ample time sort of on a one-to-one basis, but if you require any additional things outside of class, feel free to just send me an email. We can sort of schedule time to meet. We can sort of do WebEx sort of Zoom chat type things. I am here really at your disposal, and you should make great use of me if you need it. So engineers, as a principle, really will use anything that makes them better at their job. We prioritize being fast and being very accurate at our jobs. And so we inherit this history as engineers of anytime a new tool that makes our job easier pops up, we adopt it and we figure out the best way and sort of most accurate way to use them. Engineers have always done math, and your parents or grandparents may have used something like a slide rule to do a lot of calculations, which was quickly supplanted by a graphing calculator or a scientific calculator, which many of you probably used in high school. And of course, now we have pretty much an equivalent, if not more powerful, tiny computer in our pockets as a cell phone, which of course does include a calculator. This course has a philosophy that I want you to use any tool that's at your disposal. As engineers, there's no limitation placed on what tools that you might use. And our open resource policy takes into account some of the newest tools, things like generative AI, things like ChatGPT. I do allow you to use it. I have no problems with you using it. Many professional engineers I know use ChatGPT as part of their job. But as you probably are well aware, it's not a perfect tool. It's a tool that has to be used cautiously and has to be used with some things in mind. So as you use and explore tools like this, both in this course and the rest of your careers, do be aware that ChatGPT should be essentially treated as just a very, very smart person you know. What that means is that they know a lot of stuff. They have an encyclopedic knowledge, just like Google does, but they do make mistakes. They are fallible. And so you can't really trust them at their word. You should always have a way to double check their answers and their results. Ultimately, we have to double check them because ChatGPT doesn't really care about us. It's not a person. It doesn't care if we fail or succeed. It doesn't care if it gives us a wrong answer. It only sort of cares that people talk about it. Make sure that you are minding your welfare and well-being, that you are double checking their work because it affects you. It doesn't affect ChatGPT. You should also be aware that if all of your work can all be done by ChatGPT, you sort of make a case to the world that there's no reason to hire you as an engineer. People should just use ChatGPT. I don't think that last point will be the case because engineers and excellent engineers are always, as far as we have so far seen, are going to be better than ChatGPT. And a lot of what you'll deal with in your careers going forward is sort of proving and demonstrating that you can use ChatGPT, but ultimately you as an engineer, as a human living, breathing engineer, are better than ChatGPT could ever be. One, we have self-correction. We can identify when we've made mistakes and we can go back and we care about being accurate. Part of this comes from the idea that we actually do care about the results of our work. We care if we give someone bad information because it might harm them, might do them wrong. And so our job as engineers is, of course, to be as smart as ChatGPT, potentially with its help, but also be creative and be ethical in how we do our engineering work. So beyond that, you are welcome and encouraged to use any tool, internet, ChatGPT, whatever it is that you require for this course, but make sure that you are doing better than what this computer program does. As I said before, this is a course that's not really designed to weed you out from an engineering path. And so this is not a course that grades terribly difficultly. But we still have to grade you to sort of keep everyone honest. And I assess you at the end of this course on 3 different things. We have a series of assignments. Roughly we'll have 1 or so a week. These are often sort of written assignments. They might be sort of little projects that we do. We'll sort of walk through them as we come to them. These are posted to Moodle, but we'll talk about them in class as well. There is a due date listed, and by and large, as engineers, it is very important that we are very timely and very prompt in our work, and so anything that is turned in late, one should still be turned in, still do the work, still get credit for it, but we'll put sort of a small 10% deduction just to help keep us honest about timelines and due dates. is ultimately sort of not all the biggest part of our class. Most of our work will be as these lab activities, and we'll do one today. These are largely sort of group-based challenges that give us practice of doing engineering ourselves. There'll be some write-up from it occasionally, but by and large, we'll be able to complete them within our class. Uh, this is the mechanism by which you can get many, many bonus points. By and large, these class activities are you get 100% for showing up and participating in the activity, and you get bonus points on top of that from excelling in these activities, winning challenges, doing particularly well. So that's a big place in which people get a lot of credit for their creative engineering. Because of the pace of this class, we don't really have time to make up a lot of stuff. So if you do have to miss something, we'll sort of count that as a 0. But again, there's many different places to get extra credit, so I wouldn't worry too much about a few absences. The biggest part of what we're working towards, and we'll say more about this in the coming weeks, is a final proposal, a final project. This is a semester-long group thing, and for the size of this class, there may be only 1 or 2 groups working on each individual project. This will sort of summarize and give you the practice of being an engineer and proposing these types of ideas. We'll say a lot more about this in a moment, but this is a large portion of how you demonstrate what engineering skills that you've acquired. Questions on very granular logistical things before we dive into a little more detail? So this final project is really learning by doing. Most of what we teach is going to be relatively general, but the place we usually learn best is by applying these concepts to actual problems that we care about solving and care about working on. This final project is going to be a proposal or a pitch of a solution to an engineering problem. You will choose what problem you work on. You will choose and come up with your own solution, and we'll sort of refine it throughout the course, sort of with the themes that we highlight. Largely, these are going to be very much solvable problems, and they're going to be an appropriate scale for you as beginning or junior engineers. So we're probably not going to tackle sort of large, incalculable problems like world hunger. We're probably not going to work on that, but we will tackle some things that are much more tractionable and equally valuable with our time as engineers. There's a few different components. We'll sort of have an interim design review, which is sort of a check-in point halfway through, just to keep progress. But the large portion of what we'll do for this final project is we'll have a written final report discussing the problem that you selected and solution that you've come up with. We'll have some element of a presentation, which we'll talk more about that as we get towards the end of this course, and some individual sort of assessment about sort of how well you upheld your portion of this group project. To give yourselves an idea of sort of what types of problems we typically work on within this final project, and ones that might start turning your gears. These are some ones that we've done in the past, and many of them try to address problems at a very local community level. It might be Bunker Hill as a community, it might be Boston in general, but they all try to hit things that we can solve in a much more tractionable way. Some places that you might find these problems are simply walking around this campus. Anybody who's walked around this campus can identify a lot of problems with Bunker Hill, many of which are appropriate engineering problems for us to tackle. Some examples of things that fall within the realm come from the participatory budgeting of some city governments. Places like Somerville and Cambridge and Boston sort of allocate some money to work on problems that the community, that the residents of these cities have highlighted, many of which are engineering challenges and engineering designs. One example from Somerville is the design for a library of things, which is like a book-based library where you can check out different materials, but this is a library of things, allowing you to check out equipment and other things that are useful but probably too expensive to purchase on your own, or you don't need it quite often. The example would be like a set of tools to fix your car, probably very hard to purchase on your own, but it's something that can be checked out from a library of things. An engineering approach to this would be to figure out what type of things go into a library of things, what tools are most useful to the average person, how do we find ones that are cost effective, how do we assure that they're equitably distributed and accessed, all of which are engineering problems of trying to allocate resources in a fair and effective way. One from Cambridge was the design and selection of these e-cargo bikes that run around Cambridge watering their various municipal trees. Very much a engineering challenge, trying to figure out how do you solve this problem of watering trees without sort of driving around a very expensive gas guzzling car. And sort of how do you deal with sort of the logistic part of labor of someone going around and having to water these trees manually. Other design challenges are things like designing an inclusive playground, one that children, regardless of their physical abilities, are all able to access and enjoy. Many of them sort of trying to deal with not just how do you create a creative, fun place, but how do you adhere to set standards like the ADA, American Disabilities Act, to design engineering within a certain set of constraints. Here on Bunker Hill, some great engineering problems that have been solved in the past is an example being the Dish Food Pantry, which is a contactless food pantry. Very much the Dish Food Pantry sort of identified a problem that they want to sort of provide resources to the Bunker Hill student and faculty and staff community, but they want to get around sort of the stigma of having to go to a food pantry or a place to access these resources. And so an engineering solution was to come up with these sort of Amazon-style lockers that allow you to sort of anonymously go and pick up materials, very much using computers and an engineering solution to come up to overcome this social problem, a social stigma. Finally, one that is on my mind a lot, and that doesn't actually have a solved solution, is that Bunker Hill, of course, has student parking, which some of you may have utilized today. But this student parking has been sold to a development company to turn into work, live, play, condo, retail places. And so as of fall, potentially spring of this coming year, there will be no student parking at Bunker Hill. How quickly that happens is sort of on the development timeline of how construction projects work. But nonetheless, there's now an immediate pressing problem. Where do you park all your students? Bunker Hill does have space. We do have land here, but how are they allocated? How is the space used? What sort of civil infrastructure planning is required to accommodate both faculty, staff, and student parking here at Bunker Hill? Very much a civil engineering design challenge, one that does not yet have a good solution to. As a look at sort of what we have in store, of course, this is a relatively short in time run through this Engineering 101. We have 8 weeks together, and we'll meet twice a week, of course. And every week we'll do something slightly different, moving through the process of coming up with a problem, which we'll tackle on Thursday, trying to define those problems and assemble a team to begin to come up with solutions, work through the design, the creative design process of coming up with ideas, but ultimately testing those ideas to see whether or not they solve the problem that we're interested in. And of course, moving through the part of now that we have a solution, we want to figure out, is it an ethical solution? And how do we tell people about the work that we've done? Some highlights and things to pay attention to. Our third week on 6/18, we'll sort of kick off our final project proper. This is when we'll sort of form our teams as they are, and we'll begin to brainstorm and sort of pick the problem that we'll be working on. So that's an important day to make sure you don't miss. We have a decent amount of work with some programming. We'll have a tournament, programming-based tournament on the 2nd, as well as some work with Arduinos towards the end of this course. We have our final project presentations on the very last day of class on the 25th. And currently there is a field trip planned sometime this semester. This course is covered by a grant from the Department of Transportation, uh, which one has waived course fees, but also has sort of given us access to a research consortium out at UMass Amherst that has invited this course as well as other students this summer to sort of play around with some of their traffic and transportation simulator testing tools. Right now that is still being finalized, but we will likely have a field trip at some point through this course. So some of these dates might shuffle, but these are sort of the class schedules as is. So as I just mentioned, this class is sponsored by a Department of Transportation grant, and so we do have a little bit of a light theme, a sort of slight emphasis on transportation safety. Many things that will touch base on sort of resources from this New England University Transportation Center, this inter-college research consortium, but it should be true, and hopefully you have found the same, that your tuition fee should be waived for this course, as well as if you leave this course with at least a C or better, you'll get sort of a $600 credit for subsequent semesters here at Bunker Hill, which I expect everybody to be able to leave with certainly a C or better. I don't myself don't manage this grant, so if you have specific questions about this grant, we can pass that along, or you should coordinate with Suman Mukherjee or Krista Reichert, who are the people who are running this particular grant. All right, last little bit of things is sort of my imploration that you should ask for help if you need or you have questions. You can send me emails, you can send me texts. Don't call, I don't answer my phone. Make sure you meet your classmates. This, again, is a very small course, even with the people not quite here today. So make sure that you do get to know each other. These are important resources as you move forward. And Bunker Hill does have a number of different support services, things like, again, the Dish Food Pantry, which I strongly suggest you take advantage of. Logistical questions, procedural questions before we talk about engineering in actuality. Wonderful. So, this first class today, we're going to figure out a little bit about what engineers actually do and to sort of align our expectations with sort of how I, as an engineer, think about the work that we do. Ultimately, engineer is an applied science. We take many science classes, we know a lot of science, but our work really comes into play by applying that, by using that information to solve real world problems. The way we solve problems is rational and data driven. We sort of use math and evidence to make decisions about how to solve problems, or as well as what types of problems are worth solving. Our work really does begin like many scientists. We spend a lot of time analyzing problems, making sure we understand what is it that actually needs fixing. How do we try to tackle a core issue or something that is the core cause of the problem that we see? We spend a lot of time in sort of this creative aspect of designing a solution to this problem we've analyzed. We usually have to work in and balance a couple of things. Of course, we're limited by technology, by what science and physics allows us to do. We're usually limited by money. We have to be economically efficient. We can't spend large amounts of money to solve a relatively small problem. And we also have to work within the realm of people. Many great engineering solutions have fallen flat because they haven't accounted for how people actually interact with their technology. And a great example is that Google once thought that people would love to have computers that they wore on their faces, so they invented Google Glass, a little handheld or a little heads-up display computer that you wore on your face. That was a great engineering solution, worked within technological limits, but no one wanted to wear them because they were ugly. And so that technology fell flat because of this sociological constraint and barriers. People have to want to use the solution that you've come up with. We can only figure out what works within technology, money, and people's opinions by testing and iterating, and that's something we'll do throughout this course as well. The last thing, of course, is that we have to actually implement those solutions. Anything that we do can't just be a theoretical idea that sort of sits in a folder. We have to push it out to the people, and that is a tricky process for many scientists, and things that we will practice here today. We as engineers work on really many different types of problems. We work on big problems. One of the really most pressing problems we as engineers work with is, of course, the issue of climate change, of which we are moving increasingly from a position of trying to prevent climate change to a position of trying to deal with the climate that has already changed. One big sort of very controversial aspect of engineering is the idea of geoengineering, which is something we'll talk a lot about towards the end of the course when we talk about ethics. But it's sort of this big engineering idea that if we simply want to decrease the amount of heat that is trapped in our atmosphere, causing a lot of climate change, why not simply reflect more of that sunlight back out into space? And there's different ways that we might do that. We might do relatively simple things like painting the surfaces of roads or rooftops white that reflect more sunlight back out into space. We might do something more like trying to seed more clouds that again act as giant reflectors. But as engineers, we work on even more outlandish and large solutions to large problems like creating sort of reflective aerosols out in the lower atmosphere, which is very controversial for the additional environmental damage it is likely to cause, as well as even more extreme large projects like putting a giant reflective mirror out in space at a Lagrange point to literally just reflect sunlight away from Earth in a very obvious manner. But we work on all these types of problems at various different scales. How we do that is, of course, what we work on throughout this course. But a lot of wonderful engineering, and in some cases, much more practical, applied, impactful ones, are engineering solutions to smaller problems. One of sort of the great places that engineers came in during the peak of the pandemic was to use engineering tools like 3D printing, things that could rapidly manufacture small parts and devices to print mask aids, things that sort of lifted the straps off of your ears so that doctors and nurses and first responders were more comfortable, more effective as they helped patients, as well as printing things like this diverter valve that allowed the respirators that helped keep people alive to help keep more people alive. All these things, very much small, simple solutions, tiny plastic parts, but ones that were instrumental in saving lives and done by engineers with very simple tools, ones that we ourselves have access to even at this stage in our career. So we work on both big and small problems. We usually start by practicing on small problems before we work our way up to the larger ones from there. A lot of what we do is sort of a very universal thing. We sort of all have a similar approach to solving these types of problems. And being an engineer is sort of inheriting a philosophy of how we approach these problems, which we try to teach you in this course. That philosophy is really most easily picked up by certain types of people with certain types of personalities or priorities. By and large, every engineer I have met is some sort of problem solver. The YouTuber Hank Green, very much a science person himself, I have sort of phrased the way that we as scientists and engineers can spend our time is one of two ways. We can either spend our time decreasing the amount that the world sucks, or we can spend our time increasing the amount of awesome in the world. Both of it are very important, very beneficial things. But we as engineers typically work on trying to decrease the world suck, trying to solve problems. We do create awesome things. We build magnificent structures and we make things that are cool. But most of our most important work comes from trying to improve people's lives and remove the things that make people's lives worse. As engineers, we really have to care about not just being right or finding the right answer, but actually helping people and improving their lives by solving their problems. Engineers are very much data driven. We are about the details. Many people come into this engineering profession with the creativity to solve problems. But if you're simply a creative person that doesn't want to do any calculations or measure things, you probably more are likely an artist than an engineer. Engineering is very much art combined with math, and we can't avoid one or the other. But within that sort of general description of engineering, there are many different types of engineers that you might be. You may already sort of know sort of where your affinity lies, but this course is designed to give you a little bit of exposure to different types. We'll look at a few now, and our first assignment has you explore different fields of engineering in at your own pace. One of the very biggest sort of fields of engineering is mechanical engineering, very much sort of the intersection of physics and science, about that really looks at manufacturing and producing physical objects. That we do a lot of things. An example of a mechanical engineering company and mechanical engineers here in the Boston area is the company Spice, which was recently acquired by Sweetgreen. And this company produces robots that are automatic chefs that cook and prepare food, trying to eliminate the variability in the food waste by human chefs who are prone to normal human errors, but trying to automate this process that makes fast food more efficient, lower cost, lower labor, and variability there. So very much building things in the physical world based off of very universal designs of robots, computers, and mechanical devices. Civil engineers, probably the most common thing when we think of engineers, really sort of work on the physical infrastructure that exists in our public spaces. But that doesn't mean simply just bridges and sidewalks and roads. An example of wonderful civil engineering combined with environmental engineering is this project from a group of engineers at Northeastern who are working on what they call the Emerald Tutu, very similar to the Emerald Necklace series of parks here in Boston. But the Emerald Tutu is a planned artificial wetland which consists of these floating buoys, these floating little pods of organic matter, of native wetland plants and some animals, that's designed to help resist sort of these storm surges, which are increasingly more common during this age of climate change, mimicking the lost wetland that has come from urbanization. So the engineering that these civil engineers do, of course, is our normal concrete bridges and structures, but as we move towards a more sustainable future, we expand our toolbox of the way we build the things around us. Electrical engineering, of course, is sort of the intersection of computer science and the devices, the technology we use on a daily basis. Some examples of electrical engineers here in our local area is a company out of Somerville called Spark Charge that designs large portable rechargeable batteries for electric cars. A big implement and sort of a big impediment to a lot of adoption of electrical vehicles is that people are worried that they'll run out of batteries somewhere on the road far away from a charger. And so this company is trying to solve this problem by producing portable batteries, just like you'd have for your cell phone, but now doing them for electric cars, which is a big electrical engineering challenge. Chemical engineering, which is where my training comes from, very much, of course, is manufacturing and making the physical materials, be they chemicals, textiles, so cloth, food, and medicine, so much more. A big aspect of what we do here in the greater Boston area is, of course, we research and we discover a lot of new drugs and pharmaceuticals, but the people who make those drugs and try to make them as low cost as possible are the chemical engineers who are trying to synthesize those materials on a very large and cost-effective scale. Biological biomedical engineering, of course, is very much applied biology. Many different examples in companies here in the Boston area, of course. But one that I always like to highlight as sort of a different take on bioengineering is this lab and group out of Tufts University, sort of one town over, who are using the principles of tissue engineering, of creating muscle and fiber and organs in a laboratory to, one, create transplantable organs so that people aren't waiting on transplant lists forever. We're also using that same technology to develop lab-grown meat as an alternative to traditional animal agriculture. Now, much of what we'll do, of course, requires a little bit of lead into, but many of us, including the three of you here, probably have some natural engineering instincts, which we hope to build upon, we hope to nurture. We will move through this design process time and time again, which really again moves through the desire to identify a problem, understand that problem, and come up with solutions, and test those solutions before we land on a formal solution. But at least as far as today is concerned, this is very much something that is often learned and practiced best by doing. And so we're going to do a little bit of a engineering exercise to at least sort of get an idea of where our engineering instincts are at this outset.